Okay. Good evening, everyone. It is my great pleasure to introduce an accomplished researcher, innovator, and leader in the field of energy storage, Dr. Sridhar sir, who, whose contributions to the evolving landscape of energy technologies are truly commendable. Dr. Sridhar sir completed his PhD in Mechanical and Industrial Engineering at University of South Africa, where he laid the foundation for his exceptional career in energy systems research. In 2017, he joined the technology division of Amar Raja Energy and Mobility Limited. For his remarkable contributions, Dr. Sridhar sir was awarded first prize for his Six Sigma project on advanced separators tailored to meet OEM requirements. Additionally, he was nominated as a young engineer by the Amar Raja Group of Industries for the prestigious Indian National Academy of Engineering in 2020-2021. Dr. Sridhar sir is a passionate researcher and has guided numerous projects aimed at addressing the energy storage needs of the automobile industry. His dedication has resulted in over 20 publications and more than 5 patents, reflecting his significant contributions to scientific advancements. His research interest includes energy materials and systems, nanotechnology, nanomaterials and nanofluids, hydrogen fuel cells and battery technologies, hydrogen production and transportation. In addition to his research expertise, Dr. Sridhar sir excels as a manager, leveraging his ability to learn and apply emerging technologies. His key strength lies in the development of new materials and machinery of multiple characterization techniques such as mechanical, electrical, and thermal analysis, spectroscopy, and microscopies, electrochemical analysis. So currently, Dr. Sridhar sir holds the position in charge of material testing and research activities in the Department of Material Research and Development at Amar Raja Energy and Mobility Limited. His leadership continues to drive cutting-edge research and development in energy storage technologies. So I would like to invite Dr. Sridhar sir for handling this session. Thank you, sir.
Okay, thank you, Dr. Ravi. Yeah, and thank you, Professor Surun, sir. So, basically, I would like to thank the previous speaker, Professor Balasubramanian sir, for laying a foundation for the characterization techniques, where he has emphasized upon the DSE and the TGA analysis. So, mostly, I will not be touching about those stuff, but I will be giving the insights about the lead acid and advanced lead acid materials for energy applications. I hope my screen is visible.
Yes, sir.
Okay. Okay.
Fine.
So good evening, everyone. Myself, Sridhar. So basically, what we do before starting this, I would like to stop the video because here for the past 3 days there is continuous raining. So due to the internet bandwidth, I'll just turn off the video. Is it okay, organizers?
Okay, sir.
Okay. So coming to the materials and components for energy storages. Here we do a lot of developmental activities at atomic scales and build up those into macro level and component level and device level and finally a battery level analysis. So at atomic level, the analysis, the characterizations we do with scanning microscopies and X-ray analysis, elemental analysis, conductivity, and XPS analysis, okay, etc. And from there, we also study the properties of those materials going into the battery applications. As currently we have a lot of objectives which I have posted here. For this is irrespective of energy, lead acid battery. Like any energy storage application, people look into these characteristics. One is better charge acceptance, high specific energy, reduced cost, higher cycle life, enhancing electrode stability, and higher efficiency in the performance, and high power density and high energy density. So in these objectives normally depends upon the active material which we use. So those active materials should have a better surface area, better morphology, better conductive network. This, of course, having the better properties will leverage in better conductivity, diffusion, and active material utilization, so that we can have a better cycle life of any devices. I'll just go through today's. Before going into this, I'll just, I think, next slide. So I'll just want to introduce about Amar Raja. So Amar Raja, we have a way or a culture. The core purpose is to build a quality of life by building institutions that provide better access to better opportunities to people all the time. We do have 5 core values, which is linked to 5 elements of our universe, like space, wind, water, fire, and planet Earth. So these 5 core values, I'll be linking this to the 5 properties for any material in this world. One is physical, chemical, mechanical, electrical, thermal. So these are the 5 critical properties for any materials is required. Like the energy behind these 5 elements, a governing factor, we have electrochemical characteristics which modifies or influences these 5 properties. So we are in 2 locations. Research laboratories in Tirupati. Another production plant is in Chittoor. So we are 1.35 billion USD revenue for financial year 24. So this is only about Amar Raja Batteries division. So now we have named it as Amar Raja Energy and Mobility. So we are in 2 locations and 9 plants we have. Around 30 million automotive batteries we produce. Around 2,500 mAh industrial batteries, and around 3 lakh metric tons of lead we are using. And 9,300 employees are there. And these are just a battery division employees, and 350 franchises across the globe. And here is a small video. Is the audio coming?
Coming, sir, coming. Audio is not coming, video is.
Okay. So this is basically about different applications where we are. So right from automotive to industrial, like solar, photovoltaic, wind, most of the sectors we are there. So this is our vision from our battery technology. So for developing sustainable green energy products and providing technology leadership in stored energy systems. That's our vision. So coming to today's agenda, as classified into 5 categories the energy storages. So lead acid battery falls in electrochemical storage system, which we will dwell more upon it today. So we'll be covering the construction and mechanism of lead acid batteries, materials, present and futuristic, with respect to alloys, separators, polymers, and additives, which are used in the battery making process. Here, I have given 4 images. This is the transformation of automotive sector. So earlier we had the two-wheelers with the kicking option, the kick rods. Now, means in the past decade, we got self-start along with the kick rod. Today, the kick rod has been eliminated and we are just left with the self-start. So this is about the batteries having lot of performance requirement in this type of segments. Now, moving from IC to EV, there are many challenges for a battery to perform. So this is about a two-wheeler, and here we have a car with ideal start-stop. If you have any latest cars, you might have seen this symbol. This is called the ideal start-stop vehicle, where we can have better fuel efficiency and lower carbon footprints in the in these type of cars. And we have this is just an example where Nissan EV has a secondary source lead acid battery connected to the primary source high voltage system, that is lithium. And this is just an example. And here we have a hybrid vehicle where both lithium and lead acid is also there as a battery pack. Coming to industrial application. So here we have the stack of batteries where these power the telecommunication sector and the home inverters, UPS segment in schools, office, hospitals, etc. And also, we are the first one to come up with the 3-tier AC for Indian Railways, having Amar Raja's battery as a pack, as a bank. So that's how the 3-tier has been implemented in Indian Railways. So this is about the topics which we are going to look upon. So giving you just a basics about the electrochemical series. So these are different metals which likes to gain electrons or loses the electrons. So lead is there, which likes to gain more of electrons and convert it to lead dioxide or lead sulfates. So basically, there are 2 types of batteries, primary and secondary. I don't want to hope everyone knows this. Primary batteries are just disposable batteries, and secondary batteries are rechargeable batteries. So, giving you a few examples of primary batteries, zinc carbon, which normally we are using like AA, AAA batteries in our homes, everything. So, Laclanche is one scientist who come up with the zinc-based disposable batteries. And secondary batteries, here are a few examples: nickel cadmium, nickel metal hydride, lithium and lithium polymer lead acid. So if you see the history of the battery, in 1800s, it started with the voltaic pile having silver zinc as a current collectors of the metal rods, where the electrolyte solution is the zinc sulfate and the copper sulfate. And then Daniel cell, copper zinc, plant A, that's the first lead acid battery has been demonstrated publicly to gain the public interest in 1859, Leclanche in 1868, 1888, Gassner, and commercial diesel, the commercial Sanger batteries in 98 and 99 of 1800s. And latest is lithium ion. Everyone, even we are also keenly working on developing these batteries into commercialization. So coming to the construction of lead acid batteries, basically we have a grid. This is made up of a metal, looks like a mesh, and also positive grid. This is also made out of a metal. It's also like a mesh. Okay. So and then an active material is pasted in these voids of the grids. Okay. And then a separator is wrapped. Either positive wrapping or negative wrapping can be done, and then stacked into a bunch of positive and negative electrodes, and then connected to the negative terminals, and then it is sealed in a plastic container. This is our basic construction of a lead acid battery. And of course, the acid used is sulfuric acid, which is filled. So this is the basic mechanism of a lead acid battery. While it discharges at the positive, at the anode, both the anode and cathode is applied of the same type of material, which is called lead oxide or lead suboxide. And when it is made into the paste and it turns into lead oxide and 3BS, like tribasic lead sulfate crystals. And at the positive, also the lead oxide remains the same, and partially when it interacts with the sulfuric acid, it converts into tribasic lead sulfate. So this is the generic process happens at the curing level. And at the formation, like as we say, it's a electrochemical storage, right? So we charge this, that nothing but formation. So we get into 100% state of charge of the battery. So at the anode, the lead suboxide and the 3BS converts into metallic lead and leaves out the hydrogen sulfide. And similarly at cathode, the suboxide converts that into lead dioxide. If we see the densities are varied here. So the metallic lead density is 11.34 grams per centimeter cube, and lead suboxide or lead oxide 9.53. Lead dioxide is 9.38 and lead sulfate is 6.29. Here we can see the densities are varying at different levels, right from pasting to formation and again charge and discharge conditions. So this means the phase transformations happens at each and every cycles in the electrodes. If you see here at the discharge condition, where the negative metallic lead converts into at the discharge condition converts into lead sulfates and leaving out 0.3 volts. At the positive, lead dioxide reacting with the hydrogen and sulfuric acid and two electrons from the negative, thus the lead sulfates and leaving water, and which it delivers around 1.7 volts. So the combination of both positive and negative, 1.7 and 0.3, gives out 2 volts. So this is how a lead acid cell delivering a 2-volt electromotive force. So now, so this is a 2-volt cell. Now, when this is connected into a series, either 2 or 4 or 6, generally in automotive applications, the electrical systems require 12-volt battery backup. So this single cell is connected into series in 6 compartments, making it a 12-volt cell. Now, as I was saying of the transformation about the automotive system, in the 4-wheeler, earlier we had just the IC engines working just with the battery just for a cranking application. So just to ignite or the combustion requirement of the fuel, right? So you can see the basic, the traditional, the requirement was this. Just the capacity, that means it should have some energy and just the combust the fuel. Okay. And in the 2-wheeler from kick to self-start. And then later, the ideal start-stop condition. Now, this ideal start-stop condition is a type of application where your vehicle will be halted in the traffic signals, and then the battery gives the energy again to start the engine of the engine of the car of the vehicle. So, but in the meantime, all your electrical equipments like AC, music system, power steering, power windows, lights, etc., should be working at that ideal condition. So, at the time, the battery will be delivering the energy. So that is called ideal start-stop condition, where you save the fuel at traffic signals. Now comes the hybrid. Here, along with this ideal start-stop requirements, here there are other requirements like the regenerative braking. Here, when you apply brakes, the kinetic energy of the wheels need to be converted into the potential energy and should charge the batteries, the discharged batteries. So these are the requirements with respect to the automotive transformation for the batteries. As I said, now I have just given you the few glimpses, a few points about the requirements. Here, you can see the elaborative requirements. In this conventional or the traditional SLI requirements, we see the capacity that should be greater than or equal to 100%, and the reserve capacity with respect to the rated capacity, it should be there, and the cranking requirements should be greater than 30 seconds, and the battery potential should be greater than 7.2 volts. I'm talking about the 12-volt system here. So these were the generic requirements. As the ideal start-stop vehicles, now with this feature, requires higher CAT. CAT means charge acceptance. That means with lesser time, the battery need to be charged. And also water loss. As I said earlier, the electrolysis happens in the lead acid battery, where the sulfuric acid is decomposed into hydrogen and sulfate ions. So hydrogen will not be there for a long time. It will just goes out. So we need to contain these evolutions. So that means more, the evolutions means more of the dry out of the batteries. So this needs to be restricted. That's why they have given 1 to 3 grams per AH. This is for ideal start stop requirement. Coming to for hybrid and deep cycle. Deep cycle also talks about the EV requirements. So deep cycles means it may be either 80% discharge or even 100% discharge. That's a deep cycle. And the dynamic charge acceptance, as earlier I was saying that. So regenerative braking, where the battery need to be charged even more aggressively. So as these evolutions are happening and the requirements are prone for the batteries to perform under very stressful conditions. So the surface area and the morphological structure of the electrodes are very critical elements. Now, there is a new requirements coming. It's called auxiliary batteries, especially designing for plug-in hybrid and electric vehicles. So what is an auxiliary battery? So this auxiliary battery is, as I given you an example in earlier slide, the Nissan EV, where a secondary battery is placed for powering the primary battery and also establishing the safety features of the vehicles. Safety features means emergency door openings, alarms, alerts, SOS, and even nowadays the vehicles are connected to cloud, the communication system, all these things. So these are the new emerging requirement, and we can see more of these batteries having a lead acid battery as a secondary power source. In India, most of the electric vehicle have lead acid battery as a secondary source to power the lithium ion batteries. So this is just a trend of the global market, how that the battery lead acid battery market is there. So of course you can see the lithium also penetration, but lead acid battery has a 11.3% average growth rate till 2030. So I'm saying why lead acid battery as an auxiliary source, because affordable, reliable, and robust performance, and the role will be very much better, most the promising in cost sensitive markets. This is the survey which has been taken place just 6 months before with around 28 automotive companies across the globe. So the requirement for a 12-volt battery, either for battery electric vehicle, that is BEV, or plug-in hybrid vehicles. Okay. So those 28 companies has given their view upon the 12-volt battery requirement. So 14 companies has laid out that the essentials need to be there. The 12-volt system should perform like key off, quiescent loads, wake up, after run, key off loads, parking lights, and voltage stabilization for the high voltage system. Okay, those are the requirements posed by those 14 companies. And 12 companies just made sure that the battery can support the required energy or not. That's all. So with this survey, International Electrotechnical Committee, this is the committee which defines a standard protocol for energy storage application. So for 12-volt, of course, this standard 600958 is in draft condition. Probably by March 2025, this may get freezed and finalized. So their proposal is they have categorically made sure that 12-volt system should either function in the modern automotive batteries, except the cranking of the engine, that is a category 1, or just provide the safety relevant thing as a category number 2, or 3, like micro hybrid cycles like starts up, which I was earlier mentioned. So category 3 categories has been made. So giving you just an idea about how an auxiliary battery performs in the real time. As of now, Amaraja is the only company working on this. And even I can say our competitors are behind us. If you see here, the marked round one, this is the generic traditional or the ideal start-stop batteries or little advanced batteries requirement is. But for the auxiliary, you can see the higher peaks. These are the current demands in charging and discharging conditions. So this would be very challenging for battery makers to provide a 12-volt battery solution for hybrid, plug-in hybrid or pure hybrid, pure electric vehicles. And here is the schematic diagram of battery electric vehicles, where 12 volts lead acid system is connected to DC-DC converter, and then this is helping for the traction battery. Normally, this high volt traction battery is 48 volts or more than 48 volt system. Now these batteries are made up of lithium-ion batteries. So this is the schematic diagram. So basically, these are the 3 requirements for 12 volt energy storages. One is load response and the voltage quality, especially to stabilize the high voltage traction battery, and also redundant power supply for safety functions. And also here one more interesting fact is this secondary source battery or the auxiliary or the lead acid battery should be able to recharge from the lithium ion battery, and also this should be able to charge partially at any disaster related time to power this battery, the high voltage battery. Now, here is a test matrix for the testing procedures of the 12-volt battery system till 7 steps. These are basic requirements for any 12-volt battery, either for cranking application or ideal start-stop application, or even mild hybrid or micro hybrid cycling vehicles. But when it comes to plug-in hybrid and battery electric vehicles, these 2 parameters, which is 9 and 10, comes into the picture. So above these 9, these parameters are basic, which we have already discussed, like capacity, reserve capacity, cranking ability, or charge acceptance, water loss, all those things. So water loss is here, electrolyte retention, or water consumption is also one of similar to water loss studies. So when we dig deep into this, the parameter 9 and 10, so we are able to see that lead acid battery can be a more promising solution for auxiliary application. So we will see what is this charge recovery, that is the 9th step, and the 10th one, which is pulse power capability. So charge recovery and pulse power characterization. These are the two new test methods has been forced by the IEC for 12-volt battery requirements. So as of now, there was no standard till date in the whole world. So now ICS is coming with the standard. If any energy storage technology meets this requirements, then that can be having the market, I can say. So why recharge recovery? As I said, the quick recharge need to be there for the battery, even at the parking condition. This is the requirement. And pulse power characterization is, this is the similar to the earlier cold cranking applications, but here with this small current, but frequent time intervals. So this is the two things. We dig deep about the charge recovery requirement. We see with 120 minutes, the battery should, that means within 2 hours, the battery should reach more than 65% of SOC. That means 65% charging should happen. This is quite challenging even for lithium-ion related storage systems, where the minus 18 degrees centigrade, this is the temperature where these batteries need to be responsive. Okay, if at that temperature it is not responsive, then mostly the battery not be selected as an ideal solution for electric or plug-in hybrid. So coming to the pulse power characterization, here it is based upon the state of charge of the batteries, 100%, 50%, 80%. The 80% not yet been determined. So by March 2025, this may be freezed at 100% SOC at small current rate, like 0.2 amps. It should be greater than 11.9 volts. The 12-volt system should be more than 11.9. And at 0.4 condition, it should be more than 11.3 volts. Similarly, at 50% SOC condition, it should be greater than 10.3 volts for 0.2, and 0.4 current condition, it should be greater than 9.3. So these challenges are not that difficult. These are achievable. So the charge recovery and the pulse power characterization normally depends upon the two parameters, which is called conductivity and DCA, that is dynamic charge acceptance, and cold cranking ability, CCA. So the conductivity most depends, while seeing the test profile or the requirements where the batteries are subjected to, we have identified the 4 segments in the positive, that is the grid thickness, that means the current collector thickness, and the type of alloy for the grid, and the active material density, and the conductive nature or the conductive network inside those activity. Whereas in pulse power characterization, the negative active material density, the expander optimization. The expander is a composition of 3 materials. One is barium sulfate, second is lignin, and third one is carbon. So we will see more of advancements in those area and surface area of those electrodes to meet these requirements, like charge recovery and PPC. Now, for any energy storage devices, normally a positive electrode, negative electrode, and a separators separating those electrodes are the critical elements and the electrolyte. having the ionic conductivity. So similarly here in lead acid battery, as a current electrodes like positive or negative, we have lead alloys. There's a primary metal, and also alloying additives are there. And the active material, which is lead oxide or lead suboxide, which we have seen in the electrochemical reactions in the previous slides. So we term it as positive active material, negative active material, and the additives which influencing the performance of those electrodes, and insulators, which is the separators. Here normally there are two kinds of separators in lead acid battery. The polyethylene, PE means polyethylene separator, AGM means advanced glass mat separators. And of course polymers, these are the polymers used for the container and the covers of the batteries. In P separator is also used in lithium-ion batteries, the polyethylene separator. The electrolyte which is used is sulfuric acid, but it is not it is diluted one, not the concentrated. Generally, it is around 1.3 specific gravity. Of course, the additives for this also there to improve the performance of the electrolyte, like water loss or the electrolyte retention, or minimizing the electrolysis process. Either we can minimize or we can increase the electrolysis process, those additives. We'll be digging more deep into this now. So alloys mostly focus on corrosion resistance, like addressing the premature losses. Separators with better porosity, better uh, tortuosity is being explored. And plastics, yeah, flame retardant plastics are also being explored. And additives in all these above three there, including the electrolyte, to improve the longevity. So we are seeing about the alloys, lead alloys. So here is the evolution of different lead alloys, right from 1860. The Plante, who has used pure lead foils, and currently the lead calcium tin alloys are having most of the importance, which has been developed by East Penn, which is in USA. So this is the evolution about the lead alloys, right from pure lead to lead calcium tin. So these are the few companies, manufacturers across the globe using different kinds of alloys in their positive and negative. I've just placed here. These are all quite old, and few more alloy compositions are not being given here due to the proprietary things. So basically, in the automotive segment, for the positive, lead tin alloys are being uh, explored. In the negative, it's a lead calcium alloy. So because of the two reasons, one is low corrosion, and second is better mechanical strength. Here are a few more companies in Exide India, Tata Green India, GS USA, and MSCCs. So lead antimony alloys are normally used for inverter applications, the home inverters, what we use in our homes. These are the other technologies. So lead, as saying the lead as a primary material, like 99% lead has been used, and other 1% is tin, calcium, antimony, silver, so etc. So now, apart from lead, the Firefly, this is one company which is working on pure graphite or the carbon foam, they term it as. They have replaced the lead as a collector with current collector with this foam, and they have immensely improved the active material utilization rates, and even they have achieved better recharging capabilities. And Axiom Power is also a US based company. They have also replaced the lead grids with the carbon. So is one company which is working on copper mesh, which is coated with uh, carbon and using in their batteries. And here is one interesting thing where the metal has been replaced with plastic, but it has been coated with conductive polymers like PANI. The plastic used is ABS. The PANI has been coated along with the PV and copper, and they have almost reduced the battery weight by 75%. So this is just a prototype. These type of batteries are not yet commercialized. So the key takeaways from the alloy perspective is most of the leading manufacturers are using lead calcium tin and lead antimony in different applications. But what are the characterization techniques involved here? So the characterization techniques here, what we do here is, as I was saying about the corrosion. So we do corrosion testing. So corrosion testing, we have three types of corrosion testing. One is the gravimetric method, and the second is the TAFL extrapolation, and the third one is accelerated potential techniques. So this is the corrosion technique. So as I was saying earlier, the 5 properties, which is always I link that the 5 properties to our 5 elements of our universe. So these 5 properties, like physical property, that is the microstructure of the alloy, the grain structures or the grain boundaries. So those images I am not presenting here because confidentiality. So those microstructures we see with either optical microscopes or scanning electron microscopes with that. And hardness, we measure it. And tensile, elongation, flexural, like mechanical related tests we do. And electrical tests, conductivity, and thermal expansion we do. And all the 5, like physical, chemical, mechanical, electrical, and thermal related properties have been studied on these alloys. And finally, the corrosion, which is the electrochemical property, as is also been analyzed. So now the separators for lead acid batteries. Basically, there are 3 categories of separators: non-woven, polymeric films, and naturally occurring. So in lead acid battery and in lithium batteries, we use polyethylene separators, and in non-woven glass fiber, which is the AGM, that's absorbed glass mat, has been used in those technology. So normally PE batteries are flooded batteries, like the electrolyte will be in flooded state, where in AGM the electrolyte will be in absorbed condition. So that's a non-flooded one. So the essential property of an AGM these are the properties: the chemical stability, thickness, porosity, pore size, mechanical strength, wettability, and wicking. These are the characteristics which are required. And the disadvantages are also there of the absorbed glass mat separators, like low tensile strength when compared to the polyethylene, larger pore sizes is also there, and high compressibility, contraction wetting separator, low crush resistance, and also high cost. So these are the current issues with the separators. So the improvements, what we are working on here is AGM with high surface area, AGM with a composite, having a composite, like the glass fiber is there. Along with the glass fiber, we are trying to make with some polymer things like polyesters being included. So AGM with membrane sandwich, like coated AGM, AGM with organic fibers like cellulose, and silica loaded glass mats, like silica has good absorption properties. So these are the few concepts are being explored across. You see here the same images of traditional AGM and the polyester feeded AGM. You can see the surface which has been very well organized, and here in the traditional AGM it is very much cluttered. When we compare the properties, normal AGM is 10 times lower in the tensors, the elongation, and the 3 times lower in the tensile. So the composite AGM separators are taking the pace in this technology. So coming to the polyethylene separators, the essential properties for a polyethylene separator should be low acid solubility, good oxidation resistance, low electrical resistance, low acid displacement, mechanical strength, wettability, and impurities. Impurities should be low. Normally, in lead acid application, we talk the impurity should be at the ppm level. So the worldwide usage, we see 85% people are using the PE separator, and 15% other kinds of separators. So there are also some disadvantages with the polyethylene separator: the high cost and low compressible forces and the high internal resistance. Whereas in AGM, internal resistance are a little bit low, and that's why we may experience a few short circuits. But whereas here, due to high internal resistance, players in global space, the Owens Corning and Raman Fiber Science Limited, exploring the alternate separators. So the key takeaways from the separator point of view is, so reducing the water loss or the stratification behavior, horizontal rip profile in the polyethylene separator has been explored, is being developing stage. Right now it is a vertical profile. And in AGM, the polyester or the polyester and polyethylene terephthalate based composite agent separators are coming into place. So coming to the characterization techniques. So the characterization techniques here also involves the mechanical properties like tensile, puncture, yes, and surface area characterizations to see the pore sizes distributions in the separators. So all the 5 properties we do, and also the electrochemical property, which is the ionic conductivity or the ionic resistance of the separators we see. So coming to the plastic segment. So everyone aware about the plastics. The plastics what we use is the PPC, the polypropylene copolymer. Worldwide, that's the plastics everyone using. The key parameters or the key properties required for the plastics are good chemical resistance, good mechanical resistance, weather resistance, crack resistance, low density, good melt flow index, and good dimensional stability. These are the requirements for the plastics. So people are also trying to have the additives similarly like in grid alloys or in the separators. Here in plastics also are doping some additives to have a better flame retardant behavior or improve the mechanical properties of the plastics. Based on the function of the additive, property modifiers, stabilizers, processing aids, and property extenders, these are the selection based we normally do. Based on the properties of the additives, flame retardants, impact modifiers, UV stabilizers, and chemical resistance materials are being explored. So when we categorize the plastics, there are 6 types of plastics from polypropylene and styrene based and polyvinyl PVC or polycarbonate. These may other materials are not that suitable to the chemical, the acid resistance. So that's the reason we are having polypropylene or PPC and the ABS in our battery manufacturing process. So even in lithium, the PPC are being used, and of course the higher usage is ABS poly. So when we rank with respect to our requirement, you can say PP is the first one with respect to the properties what we require for our battery application, and second comes the ABC, third carbonate, and acrylonitrile styrene, PVC, and acryl styrene, acrylite. So these are the ranking. And few additives are being explored. Here I have listed some of them. The calcium based, especially people are highly recommending due to the plasticity and the manufacturing benefits. So worldwide we see PP with additives are being explored, and then ABS with additives being sorted by lithium ion battery manufacturers across the globe. The long fiber thermoplastics and the PPO material, the phosphorus based one. These are the two materials are actively sought out materials for polypropylene due to its compatibility with polypropylene and also the cost of the material. So coming to the characterization techniques involved here, we do the mechanical properties like flexural isoiodine tests we do on this material, and flammability with respect to UL 94 standard we follow, and DSE, TGA, thermal related stability analysis we do for different types of formulations and the different types of plastics. Now coming to additives role, these additives are primarily focused upon the active material additives. So as we know, the active material here is lead oxide, and to improve the utilization rate of those active material, that means increasing the span of those activeness of those material, we require some additives So normally these additives are 2% in weight, have been used either in positive or negative is the maximum, and the impurity should be less than 0.1%. If you see here, here I have given preparation, that is the electrode preparation process in the PAM, that is a positive active material, where the lead oxide is added with the binder. This again reacted with the sulfuric acid, and the additives here used is SPT. This is sodium perborate tetrahydrate, and for or some applications required 4BS, that is tetrabasic sulfate crystals, as an additive have been used in the PAM, that is positive active material. Whereas in the NAM, lead oxide and binder sulfuric acid are there, but expander is one critical ingredient has been used. This expander consists of 3 elements: barium sulfate, lignin, and carbon. Here, these materials are added into the pasting mixer along with the lead oxide powder, where the lead grids or the panels are included, are indented, and the pasting happens and then goes into the flash dryer and the curing chamber, where the conversion happens from lead oxide to tribasic or tetrabasic structures, and then positive flat plates and negative flat plates are being made. We'll just see the oxide preparation process here. This is the bottom part oxide preparation technique, where the lead ingot has been melted. This is the dross or the slag. This is the melted metal reacted with the oxygen and then formed as a powder. So this is the right side one is a ball mill process. The left one was a bottom. This is the ball mill, where the lead ingots are made into small balls and then rotated in desirable speed, where this lead metal converts into lead oxide powder. So this is the horizontal or the conventional ball mill equipment. So this is how a active material or the lead oxide powder is made. And we see the comparison between the two techniques, how where the lead oxide powder is made by ball mill method and the Barton method. I hope my cursor is visible, or should I use the pointer?
Visible, sir. Visible.
Hello? The cursor is visible. Okay, right. So if you see here, the ball mill method, the particle size is around, sorry, this is my mistake. This is not mm, this is microns. So the average particle size is 2 to 3 microns, and the bottom part is around 3 to 4 microns. So as we know, higher the particle size will have lower surface area. Lower particle size will have higher surface area. You can see here. So we have both the process, and mostly in the whole world have these two processes, and these two processes are made with respect to the application. For stationary applications, the bottom part method are used, and for automotive and for like quick charging, quick discharge, for that we use ball mill technique. So here is the paste mixing process of the active material preparation. is the lead oxide powder is mixed with either SPTH or the 4BS crystals, or there is tetrabasic sulfate crystals, or there is in the PAM. In the NAM, the carbon lignin are mixed up here. And here the tasting process, where the grids, the mesh type grids, are applied with the taste, is the active material. The taste is the active material. And then goes into the flash dryer. The temperature around 180 degrees centigrade to remove the moisture and those contents in the plate. These are those flash dryers. And the plates are being collected by the robotic arm. Just forward it. So these are the electrodes. And after the pasting, it goes for curing. This is the big electrodes. These electrodes are used for telecom applications, railways, telecoms, industrial applications. So I'll just forward, due to the lack of time, I'm just forwarding. So there are different types of additives, the positive additives, negative additives, and electrolyte additives. I'll directly jump into the what are those additives what we use. Even globally, what people are using. This is called seed crystal, nothing but 4BS crystal. People sometimes term it as tetrabasic sulfate crystals, used for cranking application. Titanium oxide, tin oxide, metal oxides, metal oxides, and red lead have been used. Sodium salts, CMC, silica, graphite have been used in the PAM additives for improving the porosity. So in the NAM additives, carbon black, barium sulfate, lignin materials we use. So coming to the carbon, so carbon has big wide group. So the allotropes have so coming to the carbon allotropes, I can classify this into basically two things based on the surface properties, like high surface area or low surface area. And also another point with respect to the pore size distribution, micropores, mesoporous, or macroporous. So we are using graphite type of materials, nanotubes. Yes, graphene under exploration. So what later a few competitors and active researchers working on activated carbon blacks, graphite, graphene, nanotubes, etc. So if you plot this with respect to the surface area and the conductivity, so lower the surface area will have lower the conductivity, and the higher will have higher conductivity. This is not always true. Okay, this is too generalized. Okay. So people across the globe working on carbon materials are listed out here. So already people are using nanotubes in their electrode processing things. And earlier we have seen the Axon batteries are making carbon-based grids. So something like that. So here is an ultra battery which has been developed by Furukawa Japan and Eastman USA CSIRO laboratory in Australia. They have developed a hybrid electrode which performs as a capacitor and also the battery. So here we are also developing some supercapacitor electrodes for application. So coming to the electrolyte additives, there are many electrolyte additives like sodium-based, magnesium, aluminum, lithium, zinc, indium, copper, bismuth, and potassium. So out of which we see the magnesium and aluminum one and also zinc. These are the three best performing materials. So other industries into the electrolyte additives are JCA, Exide, and GS USA, and Hitachi. So as I said, in the positive active material, we can classify that everyone uses binder, SPTH, and for this negative expander binder materials. So the key takeaway, the advanced carbon are being a highly sought out material across all energy storage technologies. So characterization techniques which is involved like XRD, XPS, all microscopy, spectroscopy techniques, and also the mechanical, thermal, electrical properties are also being. So I'll just give a small recap what we have just looked in. So these are the grid. Active material applied to the grid and termed as plate or the electrode, wrapped with a separator, either P or AGM separator, and then stacked up it as a group and making this 2-volt cell. Unfortunately, the sound is not coming, I think. Don't know why. Yeah. And grouping it, making it a 2-volt cell, and connecting in series, making it 12-volt battery. And then connecting the positive to negative, either parallel or series with respect to the application. So after filling the electrolyte, the formation is done where metallic lead is converted, lead oxide is converted to metallic lead in the negative, and lead oxide in the positive converted to lead dioxide. And this is the small glimpse I can cover where the all the properties, as I was mentioning, like physical, chemical, mechanical, electrical, thermal, all these 5 properties we do analyze of different composition at the material level, component level, device level, at the battery level. Of course, the battery level we listed out. I have given the electric testing, just charge and discharge, and at different environmental conditions we test, and also different vibrational condition because it goes into the automotive application. So these are the glance of testing facility, what we have, what we do every day. And also we adhere to environmental regulations, ROHS, REACH, CRMT, and conflict minerals. And these are the few national and international standards which we follow, ASTM, for materials, material testing, and product level testing. And coming to the advanced, as I say, the advanced in the material point of view. Now, as a device point of view, we are exploring to have 2 types of chemistries in one combination. That's one thing. Another thing, the ultra capacitor layer deposit on the electrodes. This may be the next coming future for battery applications. So we have few memberships, national and international. So finally, I just want to show you this video and finish it off. So here the lead ingots or the metallic lead comes to the warehouse. And then these ingots are sent to oxide manufacturing process. I'll just directly go oxide plant because lack of time. This is a complete battery manufacturing facility, I can say, in a short video. This is a ball mill outside. The flash dryer, the paste, the active material is applied onto the current collectors. Sorry. So these are manual, the old videos. Actually, everything now it is automated. Acid filling and testing happen. The formation. This is the dump and refill technology. After formation of the battery, the electrolyte is refilled with different specific gravity. This is the finishing part. The whole battery is tested and then sent for dispatch. The batteries are stretch wrapped. So I sincerely thank MVGR management for giving me this opportunity. Thank you.
Thank you, sir. Thank you. Dear participants, I think we now open the floor for any questions or thoughts you may have. Please feel free to share your queries or insights in the chat box, and also you can raise your hands.
Hello, sir. Sridhar, sir.
Hello.
Sir, when we design these batteries, are you taking into consideration EMI shielding effects, sir? Like electromagnetic interference effects, since it is continuously emits radiations.
Mhm.
So,
See, actually, the EMI shielding part is taken care by the sheet metal division
sir,
because for the when it subjected to the what you call metal casings,
sir,
so these are into the pictures, which is our sister company only. That's a
okay.
power. That's a another section is there. So those people design those EMI shielding percentages for the metal racks or the casings. So for us, the metal is lead here, so we don't deal with that metal casing, the EMI shielding process.
That means if we propose, come with any proposal, will there be any possible to collaborate with? Like if we propose material
Yeah,
for
you,
shielding,
okay.
in
See,
that case,
normally for EMI shielding, so electrostatic process is done, right?
yes, sir.
Electrostatic coating.
Yes.
So if you propose the material composition, then that would be better.
Okay. Okay.
Okay. I hope that is your area.
Yes, sir. Part of looking into it.
Composition, right? The
Yes, sir.
powder composition. So if you have any thoughts about on that, you can just contact me.
Okay, sir.
Okay. Because see, traditionally the composition has there also the carbon is there, right?
Yes, sir.
And also metal oxides are there, and also plasticizers are there. So now I am working on a different aspect, not with respect to the EMI shielding for the metal sheets, but different aspects. So you can contact me if you have a proposal for the composition.
Sir.
Okay. Yeah.
Sir, Krishna Varma garu, please.
Thank you.
Thank you.
Hello, Krishna Varma garu. You may ask.
Any
now,
other
sir.
questions? Dileswar sir.
Dileswar garu, please unmute yourself.
Sir, Dileswar sir, you can
Sir,
ask your question.
so thank you.
Hello, you can proceed, Dileswar garu. Krishna Varma garu, please. You have raised your hand. I think please may I ask your question. Any other participants, please? Naresh garu, please proceed.
Yeah, sir. Good evening, sir.
Good evening, sir. Good evening, sir.
Yeah, it's a highly informative session, sir. Actually, we learned a lot about lead acid battery from the starting to till the complete packing of the battery. It's
Thank you.
highly informative, and we learned a lot, sir, within 1.5 hour span, less than 1.5, I can say.
Sir.
Thank you very much for the information.
Sir.
Actually, myself, Dr. R. Naresh, assistant professor in the Department of Mechanical Engineering from BYRT Narsapur, Telangana.
Hello, sir.
Yeah, actually, I'm just now I completed my PhD in this August, sir, from BITS Pilani.
Okay. Good. Congratulations.
Full-time PhD. Thank you, sir. Full-time PhD I performed actually. Okay. So prior to that also I worked as assistant professor in Geetham University and other good engineering colleges. So I'm very much looking into a kind of material research that we are saying, like a material composition. Yeah. And also I worked with my my PhD research is about phase change materials for thermal management applications. I think now so many industries are working for battery thermal management using phase change materials as well.
Yes.
So I'm looking for that kind of research also.
Yeah. See, actually, all the batteries, any energy storage technology, is a phase change material. So,
Yes,
so you can ping if you have any solvable solutions with you. You can share. Definitely, we can work together.
Yes, sir. Actually, I developed a good synthesizer, some good materials which will help us to achieve the thermal management of the electronic devices like batteries, everything. So,
is this related to thermal runaway?
Yeah, thermal runaway, sir. Actually, so we can address the thermal runaway problems of the batteries. Any thermal problem where we can manage the temperature, we can use this ACM.
Okay.
So I prepared my own material in the laboratory. So
excellent.
I'm very much looking forward to that kind of work, sir. Actually, so I would like to write an email with you after this, so that I will share my expertise so that we can look forward for any collaboration possibilities.
Sure. Please send your proposal. We will just look into it.
Definitely, sir. One more thing, sir. What is your suggestion for the researchers like us to look into for this, especially for your kind of industry? What is your problems? Can you pose couple of problems where we can start
one
aiming
is
doing this kind of projects?
quick. See, normally I have not given the classification of battery and the capacitor. Have you gone through the Raman plot? If you go through the Raman plot, you can see the energy storages giving at the lower uh, power densities, especially.
Okay.
So where the capacitor has higher power density, right?
Okay.
So this is the quite challenging for all energy storage technologies to incorporate that super capacitive performance into the battery. So that is one big challenge. Maybe you can work in that dimension. So basically, yeah, all the five properties are important. Physical, as I was saying, so material characterizations, we should be very thorough with the material calculation. Then, yeah,
Yes,
there is one area. Even we are also actively working on.
In my research, I used all material characterizations, what you are mentioning. Even some more also I used actually. I am very much thorough about that characterization. Completely experimental method, sir.
Okay.
I did my 6.5 year research in materials only.
Okay.
And
Okay.
that
Okay.
I explored structure. I explored mechanical properties, non-destructive properties, and thermal properties. Everything I explored, sir.
Yeah, we can work on the power density aspect. So normally energy density, it is already known, like lithium and sodium are better. Now power density is the most sought out area.
Okay. Power density is one, and one more is Raman plot you're saying.
Raman spectroscopy, that's a material characterization part. No, that's not.
You're saying some Raman plot for this energy storage.
Okay, Rangan plot. Rangan plot. You can just Google it. You can Rangan
RONG. Can you spell, sir?
Rangan plot. RONG. Sorry.
Okay, Rangan. Okay, sir. I will go.
Rangan plot.
Rangan plot. Okay, sir. Sure, sir. Any other things which is like industry is looking forward? Some problems you. Any other problems you're looking at, sir?
Yeah, that is a one aspect. Not only me. Most of the battery manufacturers are looking into. That's the power density. That's one requirement, major requirement.
Okay. So this about thermal runaway, how it is being addressed in the industries currently?
See, like phase change materials are there.
Okay.
If you talk in lithium ion, people are having their own proprietary phase change materials to absorb those heats and everything. In lead acid, we use flame retardant materials to address these sort of aspects, and also some polyolefin materials have been used. Olefin material. Yeah.
Okay. Thank you, sir. I will be in touch with you. I'll write an email after this. Thank you, sir.
Okay. Thank you.
There is a small queries from Dr. T. Padmavati, madam, sir. Ma'am, if you want to ask any query, you can ask to sir. Sir, she is posted in some query in the text box, sir. Chat box, sorry.
So why voltage quality is considered? Why not current quality? So the voltage quality, especially in 48 volt system, there will be a lot of fluctuations. So especially which damages other 12 volt systems also. So that's the reason now the quality of voltage is being considered. So especially which I was showing the 11.3 volts and 11.9 volts at different SOCs. So at that point of time, if the battery are not having that potential, along with the primary battery, the electrical equipments are being failed. So that's the reason the voltage quality is monitored and even given as a higher safety requirement. I hope I have answered. Like power steering, like power windows, doors, emergency doors opening, even ADAS nowadays. So these
Any
requirements are there.
Any other questions from participants here?
I think okay, proceed, Dr. Kumar.
I hope everyone is clear. So, sir, it is my pleasure to extend our sincere thanks to our esteemed resource person for delivering an insightful session on advanced battery, lead-acid materials, components, and management strategies. Your comprehensive discussion on the latest advancements in lead-acid battery materials, electrode design, and innovative management strategies has greatly enriched our understanding of this well-established yet evolving technology. The practical insights you shared on optimizing battery performance, enhancing life cycle efficiency, and integrating effective management technique were particularly valuable. This session has provided a strong foundation for those involving in battery research, development, and application. Thank you once again for your time, expertise, and engaging presentation. We are looking forward to learning from you in future sessions. Thank you so much, sir.
Thank you, Mr. Thank you, MBA management team, and also thank you, Professor Subramanian sir, for giving me this opportunity to share the insights of the advancements in lead acid.
Thank you, sir.
Thank you.
On behalf of everyone, I would like to thank you for your detailed and insightful presentation on the materials and management of lead acid batteries, fabrication and characterization techniques, and particularly the role of auxiliary batteries. So your discussion has provided valuable insights into how these components contribute to vehicle reliability as well as innovation. Thank you once again, sir, for sharing your expertise.
Thank you, sir. Thank you.
Sir,
Welcome.
sir, kindly hold for 20 seconds, sir. So we are taking that screenshot. So dear participants, kindly switch on your video so that we can take that screenshot. Yeah, thank you for your kind cooperation. So thank you, sir.
Thank you.
So
Thank you.
session. Thank you for
Thank
sharing
you.
your insightful thoughts.
Thank you, and all the best for further sessions. Thank you.
Okay. So dear participants, I hope everyone is got some knowledge from that our esteemed experts. So tomorrow, so there is one more. There is two more sessions are available. The first session is handled by Dr. Radha Manohar sir. So he is from University of Chile, which is having that US world ranking below 150. So he is an eminent distinguished researcher in the area of nano generators, piezoelectric materials. So I hope everyone will join tomorrow as early as possible. Uh, Thank you so much, sir. You can leave the session, sir.